So this was hopefully, I know we just briefly went over it last time. Hopefully it'll make sense going forward here. I don't know why these are all taped together. So we have star A, B, C, D, and E. And I would say the first thing you should always do is identify where on the HR diagram they go. So again, to do that, we look at the temperature and the absolute magnitude. So the absolute magnitude of 10 and 2800 puts the star right about there. So that would be star A. Star B, 5800 and 4. 5800 is about here, and a 4 is about there. So that would be star B. Star C, 27,000 and -7. 27,000 is here. -7 is about there. So there's star C. Star D is 3,000 and -5, so that would put it there. And then star E, 18,007 puts it about right around there. There's star E. Okay. So going forward from this, the first question is, which of the following stars is the brightest star? So when it says which is the brightest star, you look at the absolute magnitude. Remember, absolute magnitude is the brightness from 10 parsecs away. So looking at their absolute magnitude, the next thing I do is say, well, which is the smallest number? Because remember, the smaller the number, the brighter it is. So the answer to the first one is star C. Okay. Then we look at, these are all like this. We look at which of the following stars is a supergiant. That's why I did this in advance, as I have right there. I can see star D is a supergiant. So the answer is star D. Then I go, which of the following is the closest to Earth? So for this one, this is where I need to compare the apparent magnitude and the absolute magnitude. And if I look at star A, these two numbers are equal to one another. So I know that star A is exactly 10 parsecs away from the Earth. It looks the same from Earth as it does from 10 parsecs away. Star B, if I look at this -11, that is a smaller number. Smaller number means it appears brighter, and it appears brighter because it is closer. So I know star B is closer. If I look at star 7, the -7 is brighter than the 3. So this one looks dimmer, and that's because it is farther away. Star D, a -2 and a -5. The -5 is the smaller number. So once again, this one appears dimmer because it is farther. And then star E, the 2, is a smaller number. So this one is brighter. And that again is because it is closer. So star E and star B were both closer than 10 parsecs. But then I have to figure out which one of those two is the closer. And then so I'm going to say, look at the difference between these two numbers. The difference here is 15. And I look at this one, the difference here is 5. So again, if I kind of think of a number line, this is 10 parsecs away. Here's the Earth. And then I think of this as being like a number line kind of going out from the 0 line. If I look at star B, it is closer, and I would go 15 of these little tick marks in. So star B would be here, and then star E would be 5 of those tick marks in, so there. Okay, and then if I were to continue to go on, which I'll do it really quickly because I already started, star A would be on that line. It would be exactly 10 parsecs away. And then I would look at star C and D. The difference here is 10. The difference here is only 3. So I'd go 1, 2, 3. So then I would have star D. And then I would go out to 10. And I would have star C. Okay. That's how you put those in order like that. Okay. So the answer down here, which star is farthest from the Earth? Oh, I thought it asked closest. The farthest from the Earth would be star C. Is that good on the warm-up? Okay. So coming over here, I want to go over this again really quickly. You will be given this formula. Okay. Um, and I will probably also write it simplified like this. Okay. So again, the way it's written out, it says the lifetime of the star compared to the lifetime of the sun is equal to the mass of the star compared to the mass of the sun divided by the luminosity of the star compared to the luminosity of the sun, which sounds like a lot of work, but it all boils down to the lifetime is equal to the mass divided by the luminosity. So you kind of simplify it in that manner. And I'll kind of come back to this in a minute. But basically, again, these just represent your ratio. This is not going to be on the exam, but it's something I wanted to mention really quickly because it was mentioned before in one of your things. That Cepheid variables are another way of determining the distances. Just look on there and you'll see where you are. And so these are stars that vary in brightness over time. And so they kind of puff up and contract, puff up and contract, puff up and contract. And they do so at regular intervals. And if we know that interval, we know the absolute magnitude. We can look at them and know their apparent magnitude and do what we just did to determine how far away they are. So it's just another way to determine distance in addition to parallax and also supernovae. So I wanted to go over this real quick. It's just a quick little animation here. So again, this shows the HR diagram. Stars down here are less massive than the sun. The mass increases, they burn hotter and brighter, and they change color going up to blue. Then we've got our giants and our supergiants, and then our dead stars down here. This was kind of a cool little, it's called Star in a Box, but just to kind of show a couple things. I wanted to put it on, I'll go on fast. So a star like our sun right here, and it kind of shows the path that it follows over time. It's on the main sequence. It will slowly over time get bigger, get colder and brighter. And then it will very quickly die and become a white dwarf. But if I click on the mass of it, I thought this was kind of a cool thing to show. Right now it's saying 1 time the mass of our sun. So if I hit play, you will see that this number changes, but very, very slowly. And then it kind of accelerates in how it changes. And I can kind of click on any point in here. So right here, I can see that the mass of the sun is still 0.997 times what it was. It lost 3/1000ths of its mass, and that was basically in 10 billion years. So 9,999.4 million years is basically 10 billion years. And it only lost 0.003 times its mass. If I come up here, it's lost a lot in just adding another few 100 million years. It lost a big percentage of its mass. Anyone know why that would be? Why would it lose so much mass? And look at the size of it here compared to its size here. Why would it lose mass as it gets bigger? Nobody? Yeah?
Is the fusion process speeding up? So like more of its matter is turning into.
Yeah, so it in order to maintain that huge size, it is fusing much faster. And so you can kind of see right here, it puffs up. Gravity is trying to squeeze this thing down. In order to maintain that huge size, it is fusing very, very rapidly. And so when by the time it gets down here, it's about half the mass that it was. Okay. And then, so again, you can see that that's just about 11 billion years to go from where it is now to where it kind of ends. Again, if I increase the mass, let's just go to 4 solar masses. You can see it starts up much higher. It goes through the same process, but you can see that it happens much more quickly when I come over here. I'm only at 200. So right there, I'm at 12 billion years. But if I come to let's come to here. Come on, there it is. That was only 215 million years to get to where it was just about to blow up. Okay. So I just want to show that quickly just to show you the change in mass. And again, kind of looking at an HR diagram. Main sequence, fusing hydrogen into helium. As they get older, they become a giant or a supergiant where they're fusing helium into other elements. Giants end at carbon, supergiants end at iron. White dwarfs mark the death of a star, if you will, where they're no longer fusing anything. Giants become white dwarfs. Supergiants become black holes or neutron stars, depending on their mass. Okay. So coming over here, this again is that formula sheet. And so again, kind of putting it in simpler terms, it is mass divided by luminosity. And so we did the first one together last time. So what I would do is call up your stellar lifespan sheet if you don't already have it up, so that you can kind of look at what the answers are. I'm not going to go over every single question, but if you have a question, I will certainly answer it. Yes? Yes. So coming over here, let's just go look at number 2 real quick. So what is the lifespan of a star that has a brightness of 0.3 L solar? So basically that's just saying this number right here is 0.3. And a mass of 0.6 M solar. That's just saying this number right here is 0.6. So if I want to know how long it lives, I just do 0.6 divided by 0.3 and I get 2. But it's not 2 years, it's 2 what? It's 2 times the life of the sun. And that's all you have to do for that. Just saying it's going to live twice as long as the sun. If it asks for how many years that is, just know that the lifetime of the sun, and I give you that right here, the lifetime of the sun is 10 billion years. So if I plug in 10 billion years, I just do 2 times 10, and I come up with 20 billion years. So if it asks for years, and you can leave it like that, you don't have to write out all the zeros per billion years. You can just say 10 billion years times 2, and then you come up with 20 billion years. Okay. For this one right here, this is written a little bit differently. If a star, so I'm going to move this down a little bit so we can see. If a star is 0.01 times the brightness of the sun, that's saying 0.01 L solar, okay? Has a lifespan of 20 times that of the sun. That's T, so 20 T, just think of it like that. And then it's asking for the relative mass. So again, if I just say T equals M over L, I'm giving you the T, I'm giving you the L, and I'm asking for the M. So in algebra, if I wanted to get rid of this L at the bottom, I'm going to multiply both sides by L. And if I do that, the L's cancel out here, and I'll have that the mass is equal to the luminosity times the lifetime. So then I just plug in my numbers. The lifetime is 0.01. The luminosity is, the luminosity was 0.01. The lifespan was 20. So I just get 20 times 0.01 equals 0.2, 0.2 M. So it's 1/5 the mass of our sun. That's all that's saying, 0.2 M. Good? Okay. All right, so those are those kinds of questions. If those are difficult, let me know. Do you guys want me to do another one, or are those okay? Give me a thumbs up if it's okay. Thumbs down if you want me to do another one. All right, good. All right, so hopefully those will be okay for you. I'm going to go through this. I'm going to spend a little time on this one, and then I won't do the next one unless you need help on that, and I'll go through it. But again, I'm going to kind of walk you through how I would approach something like this. So I would definitely focus on this right here, and I wouldn't try to answer any of the questions until I did one thing, and that is make an HR diagram. And I'm going to make a very simplified HR diagram. I know that the stars at the bottom of an HR diagram are dim, and the top are bright. I know to the right-hand side they are cool, and to the right-hand side they are hot. that's just like a simplified thing. And you'll have an HR diagram on the test. So if I look at this first one to plot where they are, again, I look at the absolute magnitude and the temperature. A 7.2 and a 6,000. So 6,000 is kind of between cool and hot, but it's toward the cool end. And a 7.2 is pretty dim. So it would be down over here. So star A would be right there in the bottomish towards the right. 2800 is cool and 11 is dim. So that would put this star down here. Star B would be here. Star C, 17,000, that's pretty hot. And a 13 is pretty dim. So we have a pretty hot, dim star somewhere over here, star C. Star D, 3,000 is cool, and -6 is really bright. I would call it super bright and put it up where the supergiants are. And then 24,000 is really hot, and a -4 is really bright. And so I would put it over here, star E. And then I would just kind of remember that my main sequence kind of looks like that. My supergiants are up here, my giants here, and then my white dwarfs kind of over here. So now I'll go through and answer the questions, and I can consult this graph over here. So which star is the greatest luminosity? It'd be the stars that are highest up, but then I can just say greatest luminosity again, look at the absolute magnitude, look for the smallest number, and a -6 is the smallest number. So star D has the greatest luminosity, the greatest brightness. Which star appears the brightest? You look at the apparent magnitude, and once again, you look for the smallest number, and a -12 would be the smallest number. So star A appears the brightest. Which star is a supergiant? So instead of having to go through all the stuff, I can just look over here and I see that star D was my supergiant. So I'm done with that. It's a cool, bright star. Which star is a white dwarf? So again, I've already done that. I put it right here. Star C is my white dwarf. It is a hot, dim star. Which stars are on the main sequence? Again, I already kind of did that. I have, so I have star B right here, star A right here, and star E right here. So A, B, and E. Which stars are burning hydrogen? Remember, the main sequence are the stars that are burning or fusing hydrogen. In reality, the star D also is fusing hydrogen, but in addition to hydrogen, it is fusing helium as well. And so that's what I meant by that question. Which star is most like our sun? Our sun is a pretty cool, dim star right in the middle-ish of an HR diagram. So star A would be most like our sun. Which star will go supernova relatively soon? So supergiants go supernova. So star D will go supernova relatively soon. There is another star that will go supernova eventually, and that would be star E, because it's a really big, bright star that will eventually become a supergiant and then go supernova. Which star will live the longest? Live in quotations. So our little teeny tiny red star right over here, they live the longest. They will, even though they have less fuel, they fuse it very, very slowly, and therefore will live the longest. And so, what star was that? D. So D will live the longest. Which star will live the shortest? That will be star E, because it is a really big hot star that will burn through its fuel very, very quickly. I'm sorry? It's B? Did I write the wrong thing? Oh, thank you so much. I appreciate that. For 12, 12 is B. Thank you. Because that is the little guy down there. I was looking at the D over here. Thank you. All right. Which star is smaller, B or C? This is a hard question. So B is right here, and C is right there. Anyone have an idea of why is that doing that? Which one of those two? Give a stamp to the person that can explain why. Charles?
It's probably C, just because white dwarfs are really, really small because they go through all the gas and the block.
I agree that it is star C, and I have to find my stamp. And I'll give it to you in a second. So it is star C. So why though? I agree they have burned through most of their stuff, but why would it be smaller? Like what if you didn't know anything, if you didn't know that that was a white dwarf there, how would you know it's smaller? Just based on the evidence presented here. I'll throw out another stamp if somebody can explain. Wait, go ahead.
I guess C and B are similar brightnesses, and since it's hotter, that probably means it's more dense.
Perfect. So in order for them to have a similar brightness, like you just said, if this one's hot, that means it's got to be tiny because that hotter flame or that it should be brighter. And so in order to be the same brightness, it is going to be much smaller. Perfect. And then, so Audrey, you were going to answer the question. So wait, was that B or C? C. All right. C, because same luminosity, but hotter, which means it has to be smaller. I could also say this, if I said D or E, which one is bigger? Audrey, what would you say?
I mean, it's just the opposite effect because it's the same luminosity as E,
About?
but it's lower temperature, which means for it to be the same luminosity.
Perfect. So D is going to be bigger than E because it's the opposite effect. Perfectly said. It is a cooler star, therefore it has to be much bigger to be the same brightness. Okay. I owe you both the stamp, and I'll get you that in a second. Okay. So I already did that right there. So which color is star E, and what color is star B? E, 24,000, that would be blue. And star D, 3,000, that would be red. The two forces acting on a star are gravity, which always wins in the end, and then radiation, the outward force that's trying to push the star apart. And so gravity will always win in the end. Okay. What effect does the answer number 17 have on the star? It collapses. It implodes. It gets crunched down to a tiny point. However you want to word that. So for 19, I really asked this out of place because, oh no, I asked 19 so that you could answer question number 20. Okay. So let's put these in order really quickly. So once again, I'm gonna delete all this so I have some room here. To put them in order, again, I compare the absolute magnitude, which is how bright they are from 10 parsecs, to the apparent magnitude, which is how bright they are from Earth. I'm going to go through and I'm going to look at the apparent magnitude first. I'm just going to kind of look at that number. Do they appear brighter or dimmer? I'm going to write a B for if they appear brighter. So a negative 12 means it appears brighter. And 11, that's equal. So right there, I know that that star is 10 parsecs away. I'm always going to give you a star that is 10 parsecs away. It's easy to identify because those two numbers are the same. In this one, an 18 is dimmer than 13. A 2 is dimmer than a negative 6. And a negative 3 is dimmer than a negative 4. Okay? So when you do your negatives, kind of be careful. Just think about a negative 4 is actually a smaller number than a negative 3. So I only have one star that is closer than 10 parsecs. So getting it started is going to be pretty easy. So again, if I have the Earth, and then I have a line that is 10 parsecs away, it's pretty easy to set the first point. I'm going to put star B right on that line. And then star A is pretty easy because it is brighter, it is closer than 10 parsecs. So I can kind of go back and compare the two numbers here, and I'd come up with 19.2. So again, if I were kind of saying, use this as a number line, 19 ticks in, I would put star A rather close to Earth. And then going out again from here, star C, the difference between 13 and 18 is 5. Star D, the difference between -6 and 2 is 8. And star E, the difference between -4 and -3 is 1. So putting them in order from here, I'm going to go 1 is star E, and then 5 is star C, and then 8 is star D. Okay, so the order is A, B, E, C, D. Okay, is that good? Does that make sense? Yeah.
So for the color question, you went fast, and I don't.
Okay,
have
sorry.
it on my phone.
So for the color question, the 24,000. Again, if I look at an HR diagram, 24,000 is going to be on the hot side, and that's going to be a blue star. So this would be blue.
Will we have like a colored HR diagram?
You just have to remember two things: hot, blue; cold, red.
So it's either one of those two.
It's gonna be that. So I mean, just knowing, and just so again, kind of just knowing red is a cold color and blue is a hot color. Okay. So yeah, those are the only two. You just have to know that kind of thing. Okay. Yes, sir. Yes. I could ask a question like this: which kind of star? And so I don't think it's outside the realm of me asking. There's a red star and a yellow star. Which one is hotter? Would you know? Which one?
Yellow.
The yellow. What would be the evidence? This goes to anyone. What would be the evidence that a yellow star is hotter than a red star? It goes back to the last thing that we did before HR diagram. And we talked about light. And we talked about the 3 L's of light: long wave, low energy, low frequency. Yeah?
So your shorter wave is higher energy, which is.
So so yellow would be a shorter wave and therefore higher energy, higher frequency. Perfect. So that would be like the evidence for that. Good. All right. So I am not going to go over this right now unless so when I'm done going over it, if anyone has questions on these, I can kind of go over these. So now I just want to go through quickly the apparent size stuff, the parallax and all that, and then I'll leave it open to you for questions if you have any. So you will be given this formula right here. Okay, so that will be provided for you. Apparent size is to sighting distance as actual size is to actual distance. For this first problem, you have a moon that's superimposed behind this ruler here, and it's really hard to read, but it looks like about 1.2 centimeters. Let's just, for me, it looks like that the apparent size, this would be the apparent size, is 1.2 centimeters. Then as I read this, centimeters set to observe the full moon pictured below. The ruler is positioned 145 centimeters from your eye. That is the sighting distance. The actual distance to the moon is 384 million meters. You are given 3 things. You are given the actual distance, you are given the apparent size, and you are given the sighting distance. It's looking for the actual size of the moon. So I would just kind of fill in the things I know. I have 1.2 centimeters over the sighting distance, which is 145 centimeters, is equal to the actual size, I don't know, over the actual distance, which is 384 million meters. My centimeters here canceled out. My unit will be in meters. I'm going to cross multiply. So I'm going to have 145x is equal to 384 million times 1.2, which I will do out really quickly. So 384 times 1.2, and I'll get 460. That's 0.8000000 meters. Divide both sides by 145. X equals, and I'm going to round this off big time, 318, and then I'm rounding the rest. 1, 2, 3, 4. 3,180,000 meters. Okay. So hopefully you remember back to that, and those make sense. Again, you'll be given the formula, and you have to be given 3 out of the 4 in order to complete. This is a little bit tougher version of what I just did. So again, size is inversely related to distance. So in other words, if I look at this little red thing here, if it got bigger, that's because it got closer. If it gets smaller, that's because it got further. So I drew my little orbit over here. We have a comet that has an apparent size of 2 centimeters. When 7 AUs from the sun, what would the apparent size of the comet be when 21 AUs from the star? So again, when it's big, that would be when it's here. And then when it's over here, that would be when it's smaller. So I could write the formula like this, that the size in position 1 is inversely related to its distance. So in other words, if I call this the D1, this would be S1. And then coming over here, if I call this D2, this would be S2. And S2, like S1, is inversely related to the distance. To combine these two, it would look like this. S1 over S2 equals D2 over D1. I will give you that formula as well. Okay? You don't need to have that formula memorized. You just need to know how to apply it. So a comet has an apparent size of 2 centimeters when 7 AUs from the sun. The 7 AUs is less than the 21 AUs. So D2 is 7 and D1 is 21. And then it's 2 centimeters when 7 AUs. That's its S2, 2 centimeters. So conceptually, I should see that when it's 2 centimeters here and it comes over here, it's going to be small. My number better be less than 2 centimeters if I did it right. So when I plug in my numbers, S1, I don't know, over S2, which is 2, is equal to D2, which is 7 AUs, over D1, which is 21 AU. That's a U, promise. So then I'm going to cross multiply, and I'm going to get 21x is equal to 14. Divide both sides by 21, and I'll get x equals, or isn't that just 0.67 centimeters? And 0.67 centimeters is less than 2 centimeters. Okay. Good on that? All right. So then parallax. I will just say, We spent a lot of time on parallax and some tough parts on parallax, converting from arc seconds and arc minutes and all that. I will keep it a little bit simplified for you. But you definitely need to understand again that the reason we have parallax is because the Earth orbits around the sun. As it orbits around the sun, at one time in the year when we look at a star, we will see other stars kind of around it. And then 6 months later, it's on the other side, and we'll see these other stars. This here is the parallax angle, and we call that angle theta, and it is measured in arc seconds. If a star is further away from the sun, then that gets smaller. So you can see that that theta is much smaller than it was up here. When we did our lab, we measured this as our distance and then this, and we called that parallax. But again, you see that the two are in proportion to one another. That as the star gets farther, the parallax gets smaller. Once again, an inverse relationship, and the graph kind of shows it right here, that as the distance increases, the parallax decreases, okay? And then I just asked some questions about that and use the graph. Again, you will be given this formula right here. Remember that R is measured in parsecs and theta is measured in arc seconds. I will maybe ask for you to convert from parsecs to light years, and I will give you that conversion. But I won't have you doing like all the other to miles and kilometers and all that. But light years is fair game. Okay. So a star has a parallax of 0.7 seconds. What is the distance? Remember, distance is r measured in parsecs, is 1 divided by theta measured in seconds. So 0.7. If I do 1 divided by 0.7, I get 1.42. And again, that would be in parsecs. That's all you have to do for that. Okay? Questions on parallax? Okay. Then we got to spectra and talking about, and I would say make sure you remember the 3 L's, that if you have a long wave, you have a low frequency and low energy. So the other way of kind of saying that, and I wrote their symbols over here, that as the wavelength increases, the frequency decreases and the energy decreases. As the wavelength decreases, the frequency and energy increase. There's your inverse to wavelength. Longer wave, lower energy, lower frequency. So there was that portion of it. And then there was the identifying an absorption versus an emission spectrum, and knowing that if we compare an emission spectrum, like the elements give off, to an absorption spectrum, like the stars give off, we know the composition of the stars. Beyond the composition of the stars, when we look at these absorption lines, if they are shifted one way or the other, we know about whether the star is moving towards us or away from us. In the case over here, I see there is a large shift in the wave. And because there's a large shift, I know that A is rapidly moving away. How do I know it's moving away? Because it got shifted towards the red end of the spectrum. And red is a longer wavelength, and therefore it is moving away. If it were moving to the blue end of the spectrum, it would be blue shifted, and it would be moving toward. But most of the galaxies and stars in our universe are redshifted, which is evidence that the universe is expanding. Then we did this, and so you are going to need to do this on the test as well. Remembering that every star in the universe contains hydrogen, and therefore will have absorption lines from hydrogen. And that if we match those absorption lines up with hydrogen itself, we can determine whether or not it is redshifted. As we can see here, we did have to move our hydrogen towards the red end of the spectrum. So this star here is redshifted. Because we moved hydrogen, we also had to move helium, and we'd have to move any elements to see if they have it. Okay. Then we did this over here, that the peak line for hydrogen, the most intense line, was at about 656 nanometers. And we were able to see that galaxies will have that peak wavelength. And if we again measure a shift in that wavelength, we can tell if galaxies are moving and how fast. We use that to talk about Hubble's law. And again, Hubble's law is that as the distance to galaxies increase, their velocity away from us also increases. But we noticed that there was a whole lot of variability around this line. But we were able to draw a generalized trend line. And that generalized trend line is called Hubble's constant. The accepted value for Hubble's constant at the time is 73 kilometers per second per megaparsec. Again, what that number means is that if I know the distance that a galaxy is away, I can plug in 73 for Hubble's constant and determine how fast the galaxy is receding away from us. So if it is 10 megaparsecs away, 10 times 73 is 730 kilometers per second. I can also do that the opposite way. I can say if I know the velocity, I can divide by Hubble's constant and get the distance that a galaxy is away. Okay? And that's where I end. Okay? So that was basically what we did. We did apparent size, we did parallax, we did spectra, and we did HR diagrams. Yes?
I was looking at the review and it says angular size at one point.
So angular size is very close. We kind of skipped angular size, and because that's when you get into trig functions and things like that. But angular size is basically apparent size. So if I look at an object over here, if I call this the actual size and this the actual distance, and I call this my apparent size and this my sighting distance, you'd see that there's an angle here, and that angle is the angular size, and it's related, it's in proportion to these others. We just didn't go into that depth. But so there won't be anything on angular size, but just know that the angular size will get smaller as the apparent size gets smaller as well. So yeah, I just forgot to take that language out. Okay. Any other questions? Okay, I know I went through that quickly, and I know that you are all at different points in how well you know this stuff. So some of you are like, oh, I got this, I'm gonna ace this. And some of you are probably like, know that this is going to be a challenge. So if you have questions on anything, especially the latest stuff that we just did with the HR diagrams, I will be walking around or sitting up here or trying to make myself available to you. Yes, sir. It's 80-point assessment. So usually the assessments are like 10 to 15. So this is 80. So it's a big deal. Okay. Any other questions? All right. The rest of the time is yours to study, to review, to do what you need to do to be prepared for the exam next class. Okay? All right. Ask me if you have questions. I really want to help if you don't get something.
Can I go to the bathroom?